Hello, everyone. So today I'm going to tell you our recent work on how to boost model robustness by using a new method that we have recently. So this is based on a joint work with my collaborators at several places. So as we know, in the machine learning or deep learning business, it's very important to achieve model robustness. So for those of you who are not familiar with model robustness, the idea is that we want our model to be really stable with respect to various input perturbations. So a typical example is adversarial perturbations. So if we simply just take a clean image, like this king penguin there, and then we just blur it. So here we use adversarial perturbations, so some artificially crafted perturbations that will fool the model effectively. And this will make the model to go crazy and give you some nonsense, like panda here in this case, and with quite high confidence. So this is the thing that we want to avoid in machine learning or deep learning, especially when it comes to productions. So these two are the papers that I like a lot, that explore all these topics concerning robustness model. So, okay, by the way, so here we will focus on input stability. So this is what I meant by robustness. And in particular, we are going to focus on data corruptions and domain shift. So there are many works that study robustness with respect to adversarial perturbations. But the problem is that models that do really well on these adversarial perturbations does not necessarily do well when it comes to other type of perturbations, such as common corruptions, which are more common in science and engineering applications. So these are the topic that we are going to focus on, and we are going to look at classification tasks. So we introduced a new method that we call noisy mix. So before this, just to motivate things a bit, so there are many ways that people use in the literature to improve model robustness. So there are things like data augmentations, where you add extra data points to the existing data set. So this effectively made the model less inclined to memorize data points. And there are things like stability training, where you add some loss assumptions that enforce stability of the model itself. And then there's this method called mix-out, where you create new data points by taking linear interpolations of randomly chosen data points for both the input and the labels. And there's a last method of noise injections, where you simply inject noise, such as white noise, to the data, or you can inject noise to the hidden layers and inside architectures, and so on. So, so there are these four methods. So noisy mix is a method that effectively leverages the advantages of all these four methods in a single setup to boost the robustness of the model. So in our case, we're interested in deep neural networks. So it sounds simple, right? I mean, you just combine four ingredients together, you get one new method. But the thing is, it's not as easy when it goes to implementations. So you do need to exercise some, a bit care when you combine these methods. So the idea is that we start with data augmentations that use in Augmix. So Augmix is a method that leverages a diverse set of transformations to data. So then it creates a more diverse set of data that you can use for training. And it has been shown that this improves both model robustness and test accuracy. So we are going to create a data set using Augmix, and then we are going to apply mix-out and noise injections now at the level of both input and hidden layers. So we inject noise not just to the data, but also to the hidden layers. And then we're going to perform stability training. So here we use the loss assumptions, which consist of some or two parts. The cross entropy that we are familiar with, and stability objective that is based on Jensen genome divergence. So that's measure of deviations between two probability distributions. So in this case, probability distributions on the clean data and the perturbed or noisy data. So, so what is the intuition behind this? Right? So how come when we just combine this method, we get something more effective? So if you look at this from the lens of implicit regularizations, we find that a noisy mix is better in terms of smoothing the decision boundary of classifier, at least in terms of in this toy classification setting, where we had 2D data set. And in the paper, we moreover provide theory to understand the effects of noisy mix via this lens. And we also have some theory in the paper that you would like to look at. And in terms of the empirical results, we show that noisy mix is indeed very effective in boosting model robustness and also test accuracy. In fact, we benchmark noisy mix against various other methods. So we use this robust bench. It's a standardized benchmark to evaluate model robustness. And we found that for benchmark data sets such as CFAR10C, 100C, and ImageNet-C, we achieve basically top performance. So top in terms of model robustness, as you can see from the figures there. And if you want to know more details about noisy mix, I invite you to check out our paper. And if you have any questions about this method, feel free to talk to me later. With that, thank you very much.